And now in the next step, I want to take you through a typical workflow on how to process data files. So let's open a study that only contains a single recording. So here we have our recorded data. We can scroll through the data by using the scroll bar. And now we can start processing the data. And if we don't know yet where to find certain options in the Curry user interface, it's again very helpful to take a look at the workflow. For example, here in the signal processing section, we now have an option, for example, to re-reference the data. And a very typical first processing step is to perform a baseline correction. So let's do this. And by clicking on any item here in the workflow, Curry shows us where the corresponding options can be found. So now we have a baseline correction step that was added to our processing list, and we can perform a constant baseline correction. We can go ahead and also filter the data, maybe from 1 to 30 Hertz. And now as a next step, let's try to find some spikes. So we can go to seizure spike detection, set the detect method to spikes, and scan through the data. So let's do this. Now Curry has processed the file and automatically marked features that might be spikes. So let's take a look. Let's press the review button. This would be the first detection, and yes, this does look like a spike. It's a dipolar field here. In this display we can see the waveforms of all the channels that a spike was detected in. And now we can label the spike as a type 1 spike. And Curry will then keep this detection as our type 1 spike and advance to the next found detection, which looks very similar to the previous detection, so we can also label this a type 1. This looks like a different spike. We can label this a type 2 spike. This is again similar to our type 1 spike, so this is another type 1, another type 1. Yeah, maybe here. Maybe for this one the time point was not so well defined, so we change the time point so that it now can also be a type 1 spike. Same for this one, and so on. And while we are keeping spikes, we can see our event list here growing. We have our kept events of the type 1 spikes and our kept events of the type 2 spikes. And we can now, for example, select our type 1 spikes, click the averaging option, and then have an averaged spike of the 6 detections that we marked. And now let's do source localization on our marked spikes. At the moment we have not added the patient's MRI to our study yet, so Curry is just using a default standard MRI data set, but we can choose from our workflow under image data the option to import image data, and this can either be image data that comes from a file or it comes from a folder like a typical DICOM image data set would, or we can also insert image data from our PACS system. And in this example I will insert image data from a folder. Let's start with the MRI, which should always be the main modality. And the very first time we import an image data set into Curry, we will see this little import dialog where we mainly just have to accept the information that was found in the DICOM headers of the image data set. If this MRI would come from a high Tesla machine, there is a bias field correction option that removes gradient inhomogeneities from the data, but in this case this is not needed. In this step we would have to specify our landmarks, which would have to be the same as the ones that we used for our surface EEG. In this case this is very bad quality MRI, so the nasion is not even visible here. But otherwise you would be able to select the landmarks from this 3D rendering of the MRI data. And now we have our MRI data in the study, so we can use this to create an individual head model, which we can again do in the workflow, source localization, and for scalp EEG, a BEM head model would be an appropriate model. So I just click on the option here and click Start. Now the segmentation and model generation has finished, so let's look at the different compartments that were created. For example, here we have the cortex and the skin. Yeah, because of the wraparound artifact, the skin, the face is not fully defined here, but that's fine. And now we can perform source analysis. And for this we are defining the head model as the BEM head model that we have just generated. In the event list I'm making sure that I am just looking at my type 1 events here. And here now we can, for example, perform a dipole fit. We can generate a cluster of dipoles which fits a dipole in each and every event that we have selected here in our event list. Or we can also average all of these marked spikes together to get an averaged event and then perform source localization on this average. We can also mark a larger time range to get a dipole trace, where we can then see how the dipole propagates. There are also some waveforms that allow us to assess how well the dipole model fits our data, and we also have the so-called confidence volumes or confidence ellipsoids, which also show us how well defined and stable our solution is. And of course we can also display the location of the dipole in an anatomical context. Besides dipole fits, Curry supports many other source localization methods, and a typical one to be used to confirm the dipole solutions is the Essloretta current density reconstruction, which can be either computed on a grid, as we see here, or we can also compute it on the individual cortex. And we can clip the results to only see the spotlight, the highlights, and then see if the solution of the current density reconstruction coincides with our dipole solution to give us a bit more confidence on the result. And if we like to save this result, we can do so by either just saving the result as a results file that opens together with the study in our Curry database. Next time we open this, the results will be opened as well. Or we can export an image data set that contains our source localization results, and for example also push this image data set to our PAX server.